Okay, today we're going to start our new unit on quadratic functions, but before we get started, let's just quickly review what you would have learned in Math 10. And what you did in Math 10 is you looked at linear functions. So a linear function was something that is a straight line. So if you would have made a little data table last year, you would have looked at this equation, the 3x plus 4, and you would have plugged in some numbers for x. So let's suppose you put in a 0 for x, so 3 times 0 plus 4 would give you 4. Put a 1 in for x, 3 times 1 plus 4 would give you 7. Put in a 2, you get 10, and we could even do negatives. 3 times negative 1 would give you 1. 3 times negative 2 plus 4 would give you negative 2, and so on. So we can see that we get a pattern that looks something like that. And what that means is, as we do these x coordinates, those coordinates then would map to certain y coordinates. So for example, if I just do the first 3, we could write that as a little mapping diagram like that. Or we could actually plot the points. So you could have 0, 4, 1, 7, 2, 10, negative 1, 1, negative 2, and so on. We plot those points, and we would see that we'd have a nice straight line. So with these kind of functions last year, you could have plotted the points, done a mapping diagram, drawn the graph, and we'd see we always get a nice linear line. The domain was all of the possible x values. So in this case, we'd say x can be any real number, right? Because there was no limitation. X can go on and on forever in both directions. And the same thing for the range. We'd say y can be any real number because they go on and on forever in both directions as well. So the first thing is, in order for it to be a function, that means each x, so for any function, it means each x can only have one y coordinate. So each x only has one y. And in terms of a mapping diagram, each x can go to one y, so that's okay. Even if these two numbers both go to the same, right, that's okay. But what we can't do is you can't have two different y's for the same x. So we couldn't go, x can't go to 2, to 4, and to 5, or something like that. So this would be okay. That one would say is not a function. And even easier in terms of a graph, if something is a function in terms of a graph, that means we can draw a line through it. So if we put a line vertically, so we do a vertical line, it's only going to touch in one spot. So it doesn't matter where we put that line, it would only touch in one spot. So any kind of graph doesn't have to be just a nice straight line. It could be, it could be a few different things. So let's look at, first of all, let's draw another one here, and we'll decide whether they're functions or not. So if I gave you a graph, and let's suppose it was a weird shaped graph, something like this, we'd say, is that a function? Yes, because anywhere we touch this line vertically, it's only going to be in one spot. So it doesn't matter how we draw them, that would be it. Okay, so let's look at what happens when we do quadratics. So a quadratic equation basically means we have an equation that has an x squared in it. So something, let's just do a basic one like y equals x squared. So a linear was just y equals x, a quadratic is y equals x squared. So in this case now, let's kind of look at each of the ways to represent this. So if we pick a value for x, let's put in 0. 0 times 0 is 0. Put in a 1. 1 times 1 is 1. Put in a 2. 2 times 2 is 4. 3, we get 9. And now let's keep going to some negatives. If you put in a negative 1, negative 1 times negative 1 is also positive 1. Negative 2 times negative 2 is also positive 4. And negative 3 times negative 3 is positive 9. So you can see here, in terms of a mapping diagram, we're actually getting some x's going to the same y. So for example, 2, 3, negative 2, and negative 3. The 2 and negative 2 both go to 4. And the 3 and negative 3 both go to 9. So we're getting two different x's going to the same y. But that's okay. That's still a function, because each x goes to one y. We just can't have it the other way around. And if we actually draw these graphs now, if you actually plot these points, we'd have 0, 0, 1, 1, 2, 4, 3, 9, and the negative, we'd have negative 1, 1, negative 2, 4, and negative 3, 9. So if we actually connect the dots on a graph like this, we get sort of a U-shaped graph. So a U-shaped graph is what it's going to look like when we get a quadratic. And a quadratic, the name for this graph, it's sort of a special name. We call it, so quadratic, we also call it a parabola. So it's the shape of a parabola. And another way of thinking about it is we say it has the second degree. And the reason it's second degree is we have x squared. We have a 2 on the x as an exponent, so that makes it a second degree. So what that means is all of the equations that we're going to be looking at are quadratics. That means they're going to have some sort of x squared value in terms of the graph. So our general equation, so this is what we call our general form or standard form, looks something like that, where a, b, and c are just some regular numbers. So if we're to graph, let's resketch y equals x squared, so that's assuming a is 1 and we don't have a b and a c. So that was the graph we just looked at. It looked something like that. So now what we can do is we can look at what happens when we look at other types of graphs that are similar. Okay, so let's try y equals 2x squared. So if you actually graph that one on your calculator and you do it right over top, what you're going to see is it looks sort of the same, but it looks a little bit skinnier, which means we're taking that graph and we're stretching it, we're timesing it by 2, so we're stretching it vertically, so we actually make it look even skinnier than it is. Okay, let's try another one. Let's try y equals 5x squared. You put that one on your calculator, it's going to be even skinnier yet. So we're 5 times taller now, so that's going to stretch it out and make it look even skinnier yet. Okay, let's try another one. If I do y equals 0.5x squared, so you can see as we went bigger and bigger, that made it go skinnier. If you actually try 0.5x squared, it's going to make it look wider or fatter, because we've actually shrunk it in height by half, so we're twice as wide, so it gets squashed down a little bit. And let's do one more. Let's look at y equals negative 3x squared. So if you put that one on your calculator, the 3x squared makes it skinny, but the negative actually makes it go upside down. So you can see that the negative out front just makes it flip upside down. It's still a quadratic, it's just we say it opens downwards instead of opens upwards. So all we're going to look at today is when we graph quadratics, can you compare them, and can you sort of say what's going on? So let's go back to the previous page. So 5x squared is narrower than 1x squared because it opens upwards. Negative 3x squared is narrower than 1x squared, but it opens downwards. So you have to be able to understand whether it opens up or down, and that's going to be determined by that a value. If it's positive, it's up. If it's negative, it's down. If it's a big number, it's going to be skinnier or narrower. If it's a number less than 1, like a fraction or a decimal, then it's going to be a wider graph. Okay, the next thing we're going to look at is, in terms of a graph, how do we figure out certain coordinates? So when we went back to this, right, for when we had a certain equation, we could figure out the coordinates that helped us draw the graph. But what happens if we go the other way around? If I gave you an equation, so let's suppose we have 2x squared plus 3x minus 4. You can graph that on your calculator, so everybody can type that in. Okay, so use your calculator to graph this, or a good program, if you don't have a calculator handy, is go on the internet and go to desmos.com. So desmos.com gives you basically an online graphing calculator. So just type in y equals 2x squared plus 3x minus 4, and it'll give you a graph that looks something like that. Okay, so on that graph now the question is, what is a certain coordinate on that graph? So either on your calculator you can use trace, hit the trace button, or on Desmos you just use your mouse and click on a point on the graph, and you can drag that anywhere on the graph. So if you click on a point over here, it'll give you what that coordinate is. So if you drag on it, we can see that we get a coordinate at 210. Okay, and you can drag it around somewhere else. Let's go over on the other side, and we can see we get -3,5. Okay, so just by tracing on your calculator or using the program, you can click and drag. It'll give you decimals, so it won't always just give you nice perfect numbers. I kind of picked ones that worked good, but it's just as possible we can get one up here. It's 2.38 and 14.47. So we get decimals, but that's okay. Because these are functions, the points are infinite, so we're going to get decimals, fractions, whole numbers, negatives, a little bit of everything are possible. So if you're trying to figure out if a coordinate is on a graph, that's the best way. Just graph it and use the trace to see if that coordinate is on there or not. Okay, there are a couple of key features of a graph. One of them is the Y-intercept. So the Y-intercept is what is that location down where it crosses the y-axis. Remember, this is our x-axis, this one's our y-axis. So we're looking, where is the y-intercept? Where is it going to intersect the y-axis? So once you have your graph, once again you can use trace, or on Desmos you can actually click on that point. They give you that point, you can click on it, and in this case it gives you 0 and -4. So one thing that's handy with this is the y-intercept can easily be found on your graph, but it also shows up in our equation. If you look up to here in our regular equation, that -4 is already there, so we already know that that's the y-intercept. So if you go back to the original equation, 2x squared plus 3x minus 4, we know the a number, the number in front, is +2, so we know it's going to open upwards, and it's going to be a little bit narrower than normal, and then we know the -4 is our y-intercept. So we have all of those features sort of right from the equation, but obviously you could always graph it and figure it out that way as well. And I think that should take care of about it. So we got everything on there. We could also find the x-intercepts and other points of the graph, but we're going to save those. We're going to save those for later on. So that's it for this first recording. See you next time.